Good morning, everyone. Welcome to the Zero Carbon Future Pavilion hosted by the Clean Air Task Force. Thank you so much for joining us this morning. My name is Jonathan Lewis. I'm the director of CATF's Transportation Decarbonization Program. Today's event is called Unlocking Hydrogen, Pathways to Generating Clean Hydrogen at Scale and Building the Global Hydrogen Market for Zero Carbon Fuels. During this event, we will discuss why we need zero carbon fuels in a decarbonized world. We will also show you the current and projected hydrogen demand to decarbonize sectors of the economy that will need these fuels. We will learn about the importance of adopting zero carbon fuels production optionality approach to meet the hydrogen challenge and the opportunities offered by superhot rock and nuclear energy to unlock mass-scale hydrogen production. We'll also learn about commercial activities to materialize these projects and their technology readiness to generate hydrogen using these technologies. I will now introduce you to our distinguished speakers. First, we have Terra Rogers. Terra is the program director for superhot rock geothermal at the Clean Air Task Force. Terra leads CATF's geothermal strategy and technical team to make clean, safe, zero carbon energy possible anytime, anywhere. Terra has been active in the renewable energy industry since 2004 and has served as Senior Vice President, Program Director, and Consultant to companies providing pioneering services and R&D solutions in the geothermal, biofuel, and energy storage markets. We also have Carlos Leipner, the Director of Global Nuclear Energy Strategy at CATF. Carlos leads CATF's efforts to develop and implement a pathway for expanded, safe, and economic use of nuclear energy globally to address climate change and support expanded energy access. Carlo has had a long professional career in the nuclear industry with various technical and senior executive roles in the United States, Sweden, Spain, and Brazil. Carlos will also deliver a short presentation about nuclear energy and share information about the Nuclear Hydrogen Initiative, which he is co-leading and which has had an exciting international reception since its launch earlier this year. We also have Roeland, Baan, the president and CEO of Topsoe. Previously, Roeland Baan has been president and CEO of the global stainless steel company, Outokumpu, listed in the Finnish Stock Exchange. Throughout his career, Mr. Baan has held a wide range of global CEO and executive vice president positions at Alaris International, ArcelorMittal, SHV&V, and Shell. We are excited that Roeland is here because Topsoe recently announced plans to expand solid oxide electrolyzers manufacturing capacity. We'll learn more about this technology and why it is crucial to the nascent hydrogen market. And finally, Andrew Bedford is joining us virtually. He is the Global Solutions Director of Energy Transition and Hydrogen at Jacobs. Andrew has more than 20 years of experience in the energy, resource, and infrastructure sectors across 40 countries. He works with multi-sector clients globally to help accelerate their energy transition journey, decarbonize supply chains, and help them define and deliver on their net zero commitments. Andrew has vast experience on hydrogen production and supply chain projects for clients across government and the private sector. Andy will also talk to us about Jacobs' activities on geothermal and nuclear hydrogen projects, and also about the social benefits of deploying these technologies. And finally, we have Eric Ingersoll, the co-founder and managing director of consulting firm Lucid, climate-focused nonprofit TerraPraxis, and development company Synergetic. Eric is a strategic advisor and an entrepreneur with deep experience in the commercialization of new energy technologies. He has extensive project and policy experience in renewables, energy storage, oil and gas, and nuclear, with a special emphasis on advanced nuclear technologies. Eric develops commercialization and market entry strategies for advanced energy technologies, such as the advanced nuclear power generation, carbon capture, and zero carbon liquid fuels. Eric will reflect on these policies, why we need them to broaden the hydrogen production conversation, and what needs to happen to accelerate the commercialization of these technologies. Oh. Sorry about that. So we'll jump in here. Why do we need fuels in a decarbonized future? Today, 80% of the final energy use is provided by fuel molecules like coal, gas, and refined petroleum products. In the future, we will be able to electrify some sectors of our economy. However, despite critical efforts to expand electrification, there are many important sectors of the economy, such as heavy transportation and heavy industry, that will be challenging or prohibitively expensive to electrify. From these sectors, zero carbon fuels will be needed. The most promising zero carbon fuels are hydrogen and ammonia. So let's take a quick poll. What is the current global hydrogen consumption? 28 million tons per year? 40 million tons per year? 90 million tons per year? Higher than that? Show of hands for A. Couple for A. How about B? B? How about C? A few votes for C. Anyone think it's higher than that? Excellent. All right. Another poll. What is the predicted level of global hydrogen consumption in 2050 to decarbonize difficult to electrify sectors? 300 million tons? Any takers for that volume? 400 million tons per year? 500 million tons per year? Or higher? Who thinks it's 300? Who thinks it's 400? Who thinks it's 500? Few for 500. Anyone think it's higher? Excellent. All right.
That's why we're here.
So these are the sectors where hydrogen will be deployed in a decarbonized future. Oops, sorry. Before we get to that, I want to answer the questions. That would be appropriate given that I've already asked you. So hydrogen demand currently is around 90 metric tons per year. According to IEA, we will need more than 530 metric tons per year to meet the needs of the hard to decarbonize sectors, hard to electrify sectors that we discussed earlier. So those sectors are shown above. Several of them, refineries, iron and steel and chemicals, we currently use hydrogen for. Going forward, in a decarbonized future, we're going to need hydrogen for those three sectors, plus heavy industry, transport, buildings, electric generation, and to decarbonize the gas grid. So hydrogen can be produced through several pathways. The mainstream narrative has focused on hydrogen produced from solar and wind energy, and to a certain extent, fossil-based with carbon capture and storage. Today, we're going to broaden that discussion and look into the possibilities that nuclear and superhot rock geothermal will be unlocked to meet the hydrogen challenge. So my final slide before I turn it over to our panelists. This slide illustrates the hydrogen production supply chain, including hydrogen transportation via pipeline or maritime. At the left side, we see superhot rock and nuclear being deployed to produce hydrogen. At the right-hand side, we see the end users. So now let's talk about superhot rock, and then Carlos will present nuclear hydrogen. We will then watch a video from Andrew Bedford from Jacobs, and then Roeland Baan will talk to us about Topsoe's high-temperature electrolyzer. Then we'll move to a panel discussion. We'll kick off with Eric's insights on these technologies. So, moving on to superhot rock, and I'll turn it over to Terra. Thank you. Do you want to use this?
Good morning. I expect that most people in the room, either if they've heard of superhot rock, may not necessarily be familiar with the process. So before I get to the slide where I tell you its value proposition, tends to sound too good to be true, I'm going to show you how the process works, so you believe me. We're going to start at the top here. We're going to inject water 5 to 15 kilometers below the Earth's surface. Once it reaches its depth, that water is going to migrate through fractures or drilled conduit, and along that process pick up the heat that naturally exists in these rocks. We're targeting 400 degrees Celsius or higher. Now this heat is a byproduct of the radioactive decay happening much, much, much deeper within the Earth. And in this light, you can think of superhot rock as a distant cousin to nuclear. However, in this case, the reactor, its products, and its fuel all stay safely embedded in the core of the Earth. But geothermal picks up the heat hundreds of miles away, closer to the surface, and brings it to the top. Now, this looks a lot like geothermal today, but The secret sauce, what's really happening here, is our commitment to 400 degrees Celsius, because it's that supercritical environment that moves and changes the phase of the water beyond steam into something exponentially more energy dense. And in doing that, you take what used to be, or what is currently a well that, say, produces on average in the conventional world 5 megawatts, enough for 500 homes, US consumption levels. And when you commit to 400, you can get a 10 times multiple, 5,000 homes. Now, walking through this diagram, you can see the flow. Now we'll move up the producing leg to the surface. Once it hits the surface, it becomes beautifully boring, because this is this process that happens everywhere in the world today. You take steam, you run it over a turbine, it goes through a generator, you export electricity. There are some peculiarities and some technical hurdles that will happen at the surface, but this is the process of superhot rock. Now I'm going to shift into the value proposition. What it is, what it isn't, and what it can do for us. First, cost competitive. Early analysis indicates that this will follow a very similar trajectory to solar, where it starts out of the market, relatively expensive, and moves very quickly through innovation and mass production to a cost point that is competitive with coal and solar today. It is inexhaustible. This is a common question. Are we going to exhaust the Earth's heat? It is not possible to exhaust the Earth's heat. Less than 0.1% of the Earth's energy today can power our current full energy demands worldwide for 2,000 years. It is, and this is a key I'm going to repeat a lot when we get into the hydrogen part. It is firm, 24 hours a day, 7 days a week, 365 days a year. I have worked on projects that boast 99.5% availability. It is a very firm, reliable source of energy. And in saying that, it's also not hostage to the seasonal changes and the setting of the sun. This goes all the time. Now, what it is not, at this point, we do not anticipate any greenhouse gas emissions from this process. And, of course, we're going to talk a bit more about how it feeds into hydrogen in the next slide. So moving over to the final column here, what it is also is available anywhere. You can imagine the Earth's heat is truly ubiquitous. If you can drill to it, you can have it. Now, this is not available today. We have to get through drilling technologies and innovations to get there. But we're on our way. The last 2 points here are items in which I'll be covering during a talk today at noon, if you would like to hear a bit more about the technological challenges that we face today, as well as some of the energy security benefits we anticipate from this energy source. Now, in this diagram, it's a bit busy, but hang in there with me. What we know about hydrogen, particularly clean hydrogen, is that a majority of its cost of production is in the consumption of energy. So when we marry a technology that inherently brings a heat stream to the surface and produces electricity from it, the synergies become self-evident in the form of reduced costs and increased uptime in these hydrogen and ammonia producing facilities. Just a quick walk through here. You can see the superhot rock facility modeled up front with its lower loop and its ability to pull some of that heat stream in for our heating and cooling needs of our homes and industries. But happening more appropriate for this conversation is providing both electricity and heat to ammonia and hydrogen. I think that concludes what superhot is within this section. May I hand it?
Thank you, Terra. That's terrific. Next up, we're going to hear from Carlos Leipner, who is going to talk about nuclear's role in hydrogen production.
Excellent. Okay, that's page down here. Okay, so we'll talk about the role of nuclear and how it plays and it can play in the production of clean hydrogen. But I want to go back to the poll because the poll is interesting, right? So we are producing around 90 million tons of hydrogen per year today, and the expectations are by mid-century at least 530. I've seen estimates up to 1 billion tons a year. of hydrogen needed. And we hope all that, or most of that, is clean, right? So if you can imagine, most of that through electrolysis will require an immense amount of energy to produce all that clean hydrogen. So nuclear does have a great way to play into that, as we need all sorts of sources of energy. As you can see here on the screen, nuclear energy can provide different pathways to produce clean hydrogen. The most common one, as we can see here, using existing reactors is through low temperature electrolysis, well-known process through electricity. But also, we can also apply nuclear energy and nuclear reactors to use high temperature electrolysis. There are some demonstration projects ongoing now that I'll speak shortly. And then we can see some advanced reactors that can go even through a different process, which we call thermochemical water splitting, which can be even more efficient as well. So three unique ways that nuclear energy can produce clean hydrogen going forward, all that through this technology. Next slide. So, and why should we really focus on nuclear besides geothermal that Terra so eloquently advocated for? First, nuclear in terms of generation produces no greenhouse gases emissions, so very clean generation. Even when we look at the overall life cycle of a nuclear power plant, it's very comparable and very low emissions through its life. It's firm, reliable, and high capacity factor, very comparable, I believe, with geothermal. We have experience today with capacity factors in the range of 95 and above percent of nuclear power plants worldwide. So very dependent. The third bullet here is very interesting. It's very energy dense. Therefore, it requires or demands a very limited physical space to be constructed. Typically, a 1,000 megawatt nuclear power plant would require 1 square mile of space. A similar power plant based on solar would require at least 75 times as much space, and wind upwards to 350 times the amount of space. So yes, we need them all, but there are different applications perhaps that we can leverage. As I mentioned, it supports multiple pathways for the production of clean hydrogen. And likewise, Terra, nuclear is also very extreme weather resistant, very reliant. We've seen this in the US in recent years, both in extreme winter or in the heat of summer, nuclear power plants being very reliable. I know we've had some issues with the French fleet this summer, but there are other factors playing into that as well. But overall, globally, nuclear power plants operate very reliably under extreme weather. And we'll talk a little bit about the advanced reactors and how we can fit into this, because there are about over 400 nuclear reactors in operation today. Many of them are light water reactor based technology. And when we're looking at the advanced reactors, we're looking at different types of technologies that can provide different types of applications, including for hydrogen. And they are much smaller in size as well, which has some benefits in terms of constructability, simplification, and delivery of that as well, and flexibility of operation as well. As you can see here on the top half of the screen, there are the various different nuclear technologies currently in development and for advanced reactors. And what's interesting is as we look at these different technologies, they come with different characteristics of operating temperatures. And you can see on the bottom half of the screen the potential different applications that it can serve for various sectors that need to be decarbonized, right? So here you see, including for hydrogen, both, as I said, for low temperature electrolysis, but even at the high temperature electrolysis and water, thermochemical water splitting, which will require much higher temperatures. You have reactors in development that can deliver that kind of characteristic. There are a few demonstration projects already ongoing in the world today, so this is quite interesting. In the United States, through the support of the U.S. government, the Department of Energy, there are many projects ongoing. So I'll mention two. In the West, there's the Arizona Public Service at the Palo Verde station. They have a low-temperature electrolysis project ongoing. In the Northeast, in New York, the 9 Mile Point, they also have a low-temperature electrolysis project being planned. And at Perry Island at Xcel Energy, they're planning a high-temperature electrolysis, which is also being, there's another demonstration project similar to that at the Idaho National Lab, which actually in the recent months demonstrated delivery of clean hydrogen at high temperatures using 37.7 kilowatts per kilogram, which is quite more efficient than the traditional low temperature electrolysis process that requires around 53 kilowatts per kilogram. So we see a lot of potential for that. But it's not just the US. As you can see here in the map, there are projects in Europe, even in Brazil at the Angra Nuclear Power Station. They use seawater to produce sodium hypochlorite, and one of the byproducts is hydrogen. So they have been producing hydrogen for over 20 years, but it's being released to the atmosphere. Now the project is how to capture that and utilize that for different purposes. So a lot going on that. Clean Air Task Force last year initiated this nuclear hydrogen initiative, which is really a platform and a forum where we link the nuclear industry to the hydrogen ecosystem that to really promote the application of nuclear technology in the production of clean hydrogen. And this has been a wonderful platform for discussion and learnings and sharing of experiences. So if you have any questions, I'll be glad to connect with me, and we'll try to get you involved in that as well. So with that, Jonathan, I think that was it for now. We'll probably engage a little later.
Thank you, Carlos. So next up, we're going to hear from Andrew Bedford, who is going to talk about the efforts at Jacobs to use superhot rock and nuclear in hydrogen production.
My name is Andrew Bedford. I've been working in energy transition and the hydrogen space and sector for quite a few years now. So Jacobs is about 58,000 people. It's very strong across the range of sectors, so aviation, transport, rail, water, wastewater treatment, but also nuclear and space and defense. So it's very wide-ranging clients across all of these sectors asking for help with decarbonizing. And the sorts of services we're offering across the entire business is looking at the generation of clean energy. Where do you source that energy from, and then how do you move it from the place you're producing it to the place you're consuming it? It sounds easy, but it's really not. We've been working on geothermal hydrogen projects. Most of the activity so far for us has been across Indonesia. It's also been some recently in East Africa. The map on the right shows you where the current geothermal hotspots are, and maybe where there's potential synergies with solar. I think the Superhot Rocks program gives you a lot more versatility in the fact that it opens up significantly more areas of the earth for development. So if you're able to develop geothermal energy much closer to the places you're consuming it, in the US or Europe, for example, it would make a lot more sense. On the left side, there's this chart we did for one of the Indonesian projects, a smaller scale, but I think this was for a 10 megawatt electrolyzer project. But the same picture is, the same story is relevant to any size geothermal project, where because you have a high capacity factor, so high energy output, 98% typically, although we use 95% capacity factor for this geothermal project, you then need a much smaller electrolyzer. So you can invest a much smaller amount in the electrolyzer facility, any downstream plant, like an ammonia plant, to produce the same amount of hydrogen versus a solar project or solar with battery storage. So you can see the LCOH, the levelized cost of hydrogen, on the right of the chart. For geothermal baseload power, it's sort of around $4 a kilogram in this particular case. I will stress it's always location dependent for geothermal because it's often in the mountains or away from the coast. But for just basic production costs, it's around $4. It varies. When you add solar into variable power, so you need a much larger electrolyzer facility to take the surge in power in the middle of the day when the solar output is highest. And then if you include battery storage, which is very expensive, there's a lot of hype around batteries, but you need to invest a lot to store enough energy to help that plant run at full, anything near 90% plus capacity factor. So it really pushes up the cost of hydrogen. And this story applies to any geothermal asset, and also nuclear. If you're able to provide that high capacity factor baseload power, it results in a much easier life and lower cost life downstream for all the other process plant. An industry generally needs consistent, stable supply of whatever it's using as a feedstock, which is exactly what hydrogen is for gas networks or plastic production or refining. You name it, this is generally what it needs. And there's a lot of potential to expand that, or the potential to extend the lifespan of existing nuclear plants is the most capex efficient way forward. Or they'll use small modular reactors or advanced micro SMR or AMR. That's the other way this could go. The heat sources from nuclear quite often go unutilized, so there's cooling and that heat is lost. Geothermal, that's what they're doing for, is using heat to produce steam, but that's part of the reason geothermal, they're confined to those locations on that, was at the last map here. So the traditional geothermal, where the energy is near the surface, so they're confined to these locations. But if you have the superhot rock program, or there's all these new technologies coming through that maybe make use of standard oil and gas drilling technologies and directional drilling, they open up much wider areas and allow you to access the heat and the energy in far more locations. Nuclear obviously has a firm, stable supply. You can build it anywhere as well. With the new SMR and AMR technologies, they're going to be modular construction, so much cheaper to construct generally, much easier to roll out. It's not a new technology, even I'll stress that. It's been around in many ways for decades and decades. And there's lots of vessels out there that are nuclear powered, generally defense, but they do exist. Overall, it's far more efficient and it's firm supply. So that allows you to provide the steady hydrogen that the downstream industries need. And that's now getting attention for producing synfuels or low carbon fuels generally. You can feed it into refining sector to help decarbonize their own operations, which is what certainly some players in Japan are looking at right now and doing. But we just started a project. It's early days, it's concept phase, but in the UK with a consortium with funding from the UK government, where we'll be working with partners to produce hydrogen from SMR technology. The electrolyzers are obviously a key part of this hydrogen supply chain to get the lowest cost of hydrogen, LCOH. And it's the SOFC, SOEC, solid oxide fuel cell technologies, like how the Topsoe is there, you can see at the bottom on the left side in that picture. That's the one that's the most efficient when it's combined with the nuclear geothermal generally to utilize that heat, because they can operate at much higher temperatures, and that's when it's more efficient. Jacobs, because we're at the concept end or early feasibility. We see it earlier than most people, but there's definitely people very seriously considering large-scale investments in decarbonisation hubs, hydrogen hubs, and you've also got infrastructure in place in some areas like Gulf of Mexico. There's hydrogen networks, so this hydrogen from these sources that we're talking about here today, nuclear, geothermal, can just essentially plug into existing infrastructure, and that decarbonises entire areas of industry to a degree. And ammonia is similar in the US. You've got ammonia pipelines that run for thousands of kilometers. So producing green ammonia or blue ammonia as well, you could in theory just inject it straight into existing infrastructure, which really does lower the cost of decarbonizing the economy. People are realizing now that we need to develop this, and the social value angle on this. I think that's where occasionally we all fall over because we get obsessed with the technologies and how progressed and what they need to support. But if you really spell out the benefits in terms of the jobs created directly as the avoided carbon emissions, which people find hard to grasp because that's often 50, 100 years in the future. But there's much more immediate benefits to people. It could be ensuring that they still have a job at the local refinery or nuclear plant or manufacturing facility because these clean energy sources exist. And that makes people think, okay, so I have a future, my kids have a future. This is something that needs to happen in the next 10, 20 years, and they feel the urgency. My name's Andrew Bedford.
Terrific. So now we will hand this over to Roeland Baan, who will talk about Topsoe's clean hydrogen solutions.
Thank you. So actually, I'm not going to run through the slides because we have lost enough time on slides. Just a few words about Topsoe. We are an 80-year-old startup, and we have clear credentials in hydrogen. Over 30% of the world's hydrogen production goes through Topsoe technology. A third of the world's ammonia production goes through Topsoe technology. You mentioned, Carlos, the Idaho labs, that they have just proven that it's 37.5 kilowatt per kilo. We have not only proven it, we are building now a factory, 500 megawatts of an SOEC high temperature electrolyzer, growing to 5 gigawatts before the end of this decade, because we have not only proven it, we have scaled it up. Idaho is using a cell that produces just under 2 cubic meters, normal cubic meters per hour. We produce now 12 normal cubic meters per hour in a cell that is 6 times as large, 7 times as large. So we are really putting our money where our mouth is, because we have this. And then moreover, when it comes to synthesis, gas to liquids, we are the only company in the world that has running at scale, and I'm talking about 2,000-3,000 tons a day, synthesis loops in different places, and we're building a 5,000 metric tons at the moment with Exxon in the US. So that's where we come from. Now back to the high temperature electrolyzers. It is an incredible thing because, first of all, the materials compared to PEM and alkaline are just normal run-of-the-mill materials. You can find them everywhere. There's no cobalt, there's no rare earth, there's no iridium like in PEM. So it's cheap and available. None of the geopolitical issues that you would encounter with the other solutions. Secondly, even without heat integration, it's 30% more efficient than the existing solutions. But with heat integration, and I come back to what you guys are doing in nuclear and hot rock, it is 45% more efficient than the existing solutions. So you need 60% of the electrons to produce the same output of hydrogen. And this is extremely important because the biggest challenge that we have in the green transition is power availability. Just to put a bit of numbers to it, let's assume we go to 600 million tons of hydrogen, green hydrogen needed. That equates, and you can debate, but it equates to 6 to 8 terawatt of installed power capacity, green. We have today 1.6 terawatt installed over the last 40 years, and half of that is a bit less, is hydro. So the challenge to get to scale on these power solutions is enormous. So every electron we can save, we need, because it's not only the power to X consumption for hard-to-abate sectors like aviation, shipping, etc. It is the direct electrification as well. And then on top of that, the world is supposedly going to double its need for power independent of the energy transition in the next 35 years. So the challenge that we have in the world on getting sufficient power, and it has to be green power, is ginormous. So that's where our technology comes in, and that's where, by the way, I believe that your technologies come in as well, because not only is it easier to scale up and relatively cheap over time, it does produce heat. So the 400 degrees of your solution, and whatever the temperature is that comes at you, because you can play with that, can go straight into the high temperature electrolyzer and saves electrons again, because you can exchange electrons for heat. So it's very simple. So I think if you believe in hydrogen being the solution, and if you believe that after transition through blue, it's ultimately green hydrogen that will have to carry the candle, then we have a solution, and I hope we're not the only one, because we can't supply the world, right? We need to have our competitors to actually shape up a bit and come and help us out, because we need a lot of these electrolyzers.
Thank you, Roeland. Thank you, Terra. Thank you, Carlos. We are going to move into a discussion phase here. I'm going to start off with Eric, who hasn't had a chance to speak yet. Eric, do you have a microphone? No. Does this one work? Yep. Here. Down there. So Eric, you have deep expertise in commercializing advanced energy technologies. Hydrogen is going to be crucial to decarbonizing key sectors of the economy, such as steel, transportation, high temperature process heat. Can you reflect on why superhot rock and advanced nuclear hydrogen are crucial to scale clean hydrogen production?
Sure. Hi, everybody. So I think I guess the first general comment is that we often see the discussion about hydrogen and electrification as if these are choices, that we have to make a choice between hydrogen and electrification as decarbonization strategies. And I think we're starting to see here today with some of the end-use sectors identified, and also with the challenges that we're seeing to kind of rolling out electrification, that we really need to be decarbonizing the system from both ends. We need a electrification strategy, and we need a complementary fuel strategy. And so, and then if we're really talking about hydrogen and broad-scale decarbonization, that's probably not just making buses run on hydrogen, or heating homes with hydrogen or whatever. It's really using hydrogen as a feedstock into chemical processes to make zero carbon fuels, which are dramatically easier to transport and use in the sectors that are difficult to decarbonize. And furthermore, if you then see the kind of massive role that could play in complementing our electrification strategies, you quickly come to an understanding that the cost of the inputs for those fuels have to be very low. We can't have $5 a kilogram or even $3 a kilogram hydrogen and make fuels from that. That's the highest oil price ever recorded in the global oil market was around $180 a barrel. And $3 hydrogen would make you synthetic hydrocarbons at about twice that. So that is not a scalable strategy for broad-scale decarbonization of these difficult to decarbonize sectors. In fact, that would make the difficult to decarbonize sectors even more difficult to decarbonize. So when you start thinking about how do we achieve this kind of low-cost, very large supply, first of all, you have to use the electricity very efficiently, as our previous speaker pointed out. And secondly, you need you need to be able to deploy large, dense energy projects to deliver that energy. And there's just one last kind of framing point that I would add to this, which is that there's something very interesting about hydrogen for fuels, which is that many of the challenges that we're having with electrification and the supply side of green electricity have to do with the challenges of deploying large amounts of generating capacity on the grid. And the problems with NIMBYism, the problems with transmission, the problems with permitting, these things are really rate-limiting steps in our economy and in our ability to deploy these things. The interesting thing about kind of centralized fuels production facilities is that they're not dependent on the grid. They can deliver via pipelines or ships to the global fuels market. And so I think that's also a way to unlock and speed up decarbonization, is to not have the same risk, which is the risk of the grid rollout, be limiting the deployment of these types of complementary solutions. I don't know if that...
That's terrific. Thank you. My next question is for Roeland. Yeah, that's the good mic. So, a little over 2 months ago, Topsoe confirmed a final investment decision on the world's largest solid oxide electrolyzer. It's going to be located in Denmark and have a capacity of 500 megawatts with expansion plans to 5 gigawatts capacity. Can you share more information around how Topsoe is planning to scale that project and projects like that around the world?
Yeah, I will. Just one remark, Eric. I agree with you on the cost of levelized cost of hydrogen, but there is another element to it, which is the cost of carbon. We are used to pay for pollution, right? We as individuals, we pay for the taking our garbage away, etc. Yet we do not pay for the garbage we put in the air. The low-cost hydrogen out of fossil fuels is not low cost. It's costing the world tons of money. And unless we're actually going to put a price on that, so to actually have the social cost of carbon embedded in the taxation of the polluter, you will not have a realistic comparison of the cost of hydrogen out of fossil fuels versus the other one. So that is the number one thing that has to happen on regulations. We need a change. We need to, because otherwise we just keep on pumping out the carbon, right? So sorry about that. I needed to make that remark. On our electrolyzer, we have decided to take this step because we have proven the concept. We have a pilot plant running on it. And as I said, we are getting to efficiencies of 40-45% with heat integration. And we think the future of that is enormous. Our biggest challenge is how fast can we actually scale this up. So 500 megawatts a year production capacity is big in the world of electrolyzer. Actually, today in the whole world, there's only 500 megawatts installed capacity. So we built something that does it every year. But it's still nothing. Fit for 55 in Europe is looking at producing using 20 million tons of hydrogen, green hydrogen, 10 million coming from offshore wind in Europe. That needs 150 gigawatts of power and 80 gigawatts of electrolyzer. And that has to be there in 6 years' time. So our biggest challenge is we need to ramp up, and we will ramp up, and we will scale up. We have investment plans in Europe. We have now plans in the US. IRA is a brilliant thing. I mean, it's a feeding frenzy. Everyone is diving onto it, us included. But it is what is needed. This sort of stuff is needed to accelerate it. And as I said earlier, SOEC clearly has an enormous advantage over the other technologies, but we need more competitors. We need other guys to go in there And we probably have to start licensing out our technology in order to get enough into the market, because we can't do it all.
Thank you, Roeland. Terra, which countries do you see as being first movers in the development of superhot rock? And do you think that development is going to be driven mainly by domestic consumption or export of hydrogen?
Well, I'll back up and say, remind everybody, this is a ubiquitous source. So in theory, available to anyone with a drill. But where we are today in technology, in terms of first movers, the low-hanging fruit are those shallow sources of heat. And I think Andy's slides did a nice job of indicating where those often are, usually around the ring of fire. They're not always where the people are. So the key here is the early stage movers, these demonstrations, are likely to find their market in both the hydrogen and the electricity. I'm going to use a couple of examples to get to your country question. Currently, Japan is doubling down on supercritical geothermal. They need this not only for the land space, but they also have that shallow heat. But we can apply that and use some of the lessons learned in Iceland, for example, where they have exported, excuse me, effectively exported their heat in the form of aluminum because they could manufacture it for a lower cost due to that price. I see the same thing happening with hydrogen in places like Alaska, who has an incredible heat endowment, Hawaii and Japan. Any place that has maritime fuel transport that could easily move. And another reason why ammonia is an important part of this conversation and other transportable forms of hydrogen. Did that answer your question?
Absolutely, thank you. Carlos, in your presentation, you mentioned the recently launched Nuclear Hydrogen Initiative, an incredibly exciting project that brings together a lot of different stakeholders in this space to confront an important challenge, a critical challenge. I wonder if you might take a little bit more to talk about what's happened since the launch, where you see NHI going, and who key partners might be going forward.
Yes, we were so excited. We are excited what's going on. But how this came about again, Jonathan. So the nuclear industry is wonderful about talking to itself, right? We talk to each other, and we see. We were talking a lot about the role of nuclear and hydrogen, but just to each other. And we understand and looked at the hydrogen ecosystem, and a lot of focus obviously on renewables as its solution for clean hydrogen. So there's this space, this gap that needed to be covered to bring the two groups together. And Clean Air Task Force at the end of 2020 gathered a two-day workshop in the midst of the pandemic. It was all done virtually. And we had hundreds of participants and demonstrating interest in the topic, and that then evolved into the Nuclear Hydrogen Initiative being formed in 2021. Today we have several working groups, one focused on policy, one on technology and R&D licensing, the other one on markets development and partnerships, and the other one in financing. And what's interesting, as you mentioned, it gathers stakeholders from across all both ecosystems, both reactor developers, supply chain, utilities, engineering firms. We have electrolyzer companies. We have end users like U.S. Steel that has talked to us and others. So it's been an incredible forum precisely to bring about and discuss the opportunities and challenges. I wouldn't say that there's a lot of challenges to be overcome with nuclear, but I think there's a lot of lessons learned as we talk about these projects that I mentioned, the demonstration projects that are occurring around the world. We are learning from each other on that.
Thank you. Well, we are approaching the end of our program, and so I want to give each of the panelists an opportunity to provide any key takeaways from today's discussion, or the discussions and efforts that you're making more generally. And so, Eric, if I could hand it over to you, and if I might, you raised some really interesting points around some of the key obstacles that the scale-up of hydrogen is confronting, including the cost of electricity, the difficult of citing clean energy technologies. Take this whatever direction you want, but I'm curious to hear if you think those challenges are surmountable, and if so, what are some key steps we need to take?
Thanks, Jonathan. I do think that that they're surmountable, but one of the things that's exciting to me, and the reason I'm on this panel, is that I feel like the project characteristics that superhot rock geothermal projects would have, namely kind of high energy density, not using a lot of land, and ability to kind of create very large projects in a relatively well-defined, small area with small land footprint, and nuclear is very similar to that. I think these allow us to have a different, there are complications with both of those technologies, and there are complications with wind and solar projects, but they have different complications. And having a portfolio of technologies that have different risks associated with them, different risks to scaling, I feel like this is really what we need. That if we sort of keep running down the road of wind and solar, we're just going to run into problems. And if we haven't developed these other technologies to the point where we can scale them, we're going to regret it. And I think the other thing is that the ability to transform these energy sources, nuclear and hot rock geothermal, that by building both of these technologies have project economics that are highly related to scale. So if you build 8 nuclear reactors at a site, the cost, is on the $2,000 to $3,000 a kilowatt level. Very, very, very attractive costs. Same with hot rock geothermal. If you do one small project, it's going to be quite expensive. If you can do a whole area, you'll have extremely low cost energy. Both of those types of projects would be too big to put on a normal grid. But if you're making hydrogen and exporting that in the form of a fuel, I think we can get around this. It also, as Tara was pointing out, Terra, you'll be able to go to places where you can start with these things and demonstrate them and build commercial models and help the global market with those. And that's so it doesn't have to work everywhere right away. We have to be able to get started and scale it and sell these clean fuel products into the global market. And that will drive adoption in other places and drive cost reduction.
Thank you. Carlos, any parting thoughts?
No, I'm I guess, excited about the opportunity. I think the numbers that we heard, right, of the demand of energy by mid-century, what we'll need, definitely points to a variety of options that we need, and nuclear can certainly play onto that. But obviously, we need to overcome the challenges with nuclear. We need to see these advanced reactors really be proven and get to the market and be successful, so that they can provide the clean hydrogen that we expect to have.
Thank you. Terra.
I think my takeaway really came from some of the statistics here that that Roeland discussed. We need to stop thinking in decades and start thinking about 2100. These are the numbers that we are not planning for. We need terawatts of energy. And if we wait and do this 1 decade at a time, we're going to be having this exact conversation in another decade. Superhot rock is already in the books in the 1970s, came up again in the 1990s, and here we are again. We need to invest now and think further than 10 years. And I like what Eric said about we don't have to do it all at once. We can use some of the lower hanging fruit through demonstrations and scale up, but we also need to acknowledge the chicken and the egg situation, which is we need manufacturers like Topsoe to produce the electrolyzers that are compatible with these heat sources, continue to find these efficiencies so that we can drive down that cost of hydrogen to something that actually addresses the demands 50 to 100 years from now. We need to invest now.
Thank you. Roland, we need lots of electrolyzers, and we need them to be highly efficient. Are we on the path?
Yeah, so I want to go at it about the other way around. We shouldn't lose the goal out of sight, which is we need to decarbonize. It's not about technologies, it's about getting carbon out of the air. The technologies that we're discussing here are supply constrained. There's no doubt. It's not demand constrained. If we had it at scale today, we would sell it. It's not there. So we need to, first of all, walk away from discussions around blue and green and yellow and what have you. It is about low carbon solutions, carbon intensity low. That's number one. And then while we bring these, because these are easy, the low carbon technologies, bio, blue, low carbon are easy, they're there at scale. We bring them in, which creates the market you need, and that gives time to us to develop at scale our technologies, because that is what is going to be the future. Wind is great, but you cannot put 14 gigawatts of offshore wind, not at a reasonable cost. Nuclear, hot rock, these are technologies that are going to be there in 2050, 60, 70. That's the future. But it will take time. And it will take time because only the scale up will bring the cost down. But we need to take that time. And in the meantime, as I said, we need to create a market by using the other technologies.
Thank you. Well, we've heard today that we are going to need at least 530, maybe as much as a gigaton of hydrogen going forward to meet the difficult to electrify sectors of the economy that could be powered by hydrogen. Scaling, therefore, will be critical to meet that forecasted demand. And we need technology optionality to scale up at that rate. Superhot rock, geothermal provide firm, clean electricity to produce hydrogen, as does nuclear energy in its many forms. We're going to need both of those, plus the other systems that we're currently using to make hydrogen, to make to reach the levels that will be needed. Topsoe scaling of solid oxide electrolyzer production capacity to meet hydrogen challenge. These electrolyzers operate at higher temperature, which makes them more efficient than low temperature electrolyzers, such as PEM electrolyzers, because it takes less energy to break down high temperature steam than water. We need the right policy frameworks to create an attractive ecosystem to move these technologies forward. A lot of work is being done on that in Europe, the United States, in Asia, and other parts of the world. A lot more needs to be done. So I want to thank the four of you so much for joining this session. I want to thank the audience for being here. I want to thank you for your terrific insights and congratulate you on the excellent progress being made in all of these areas. And I want to thank Andrew Bedford for joining us virtually. This session will be available on the Clean Air Task Force YouTube page soon. And we invite you to check out this presentation and others. And I want to again thank everyone for joining us and wish you a great day.